Hello. So this time we're going to discuss the idea behind surjectivity, and for that we're going to introduce a function, of course, because these are ideas that are associated with functions. So start with a function. Again, just as a diagram here, we have a collection A, what we call the domain, collection B, we call the codomain, and of course a label for the function, which would be the rule of the function associated with all the domain in the codomain. Right? Every element of the domain is associated with a single thing in the codomain. Okay, so what if every element of B is the output of some item in A? I'm kind of exchanging this idea that defines the totality of a function, right? Every single input has an output. What if we reverse that and say, well, now every single output has an input? Well, formally we would have the following. The following condition. For each y in B, there is x. Let me just erase this portion. There is x in B such that y is equal to f of x. So every single element of the codomain is the output of something. That's what we're indicating here. So just to make a distinction, I'll provide two examples, graphical, just as the one that we have. Let's see. For instance, if I have this blob here, right? Say 1, 2, 3, and I have this other blob, like A, B, C, D, and then, well, with 1 I associate that, with 2 I associate that, with 3 I associate that. This is certainly a function, but the condition that we are indicating just here, well, is not satisfied in this case, right? But what about this other example, right? Say that I have now this collection, right, which would be my domain, consisting of the elements 1, 2, 3, 4, and on the other side I have something that looks like this. I have A, B, and C. Then I make the following association. That one, that one, that one. It's certainly a function, but now it does satisfy this condition, right? So that one is an example of a function that satisfies the condition, FAT for 2, while the function that we're just clarifying here under example 1 is not the case that it satisfies the condition. Okay, now, can we gain some intuition about the numerical relation between A and B? Meaning, can we compare the number of elements by having this condition available? Well, let's do this. And I'll start with the process. Something that we have to notice is that the removal here, say, the condition is satisfied. Well, the removal of an element of B results in the removal of one or more elements of A. Of course, associated elements through the function, right? Moreover, removing each element of B results in the exhaustion, right? In the removal of all the elements of A. But something that we have to, and why is that this happens? Well, because we have a function, right? Every single input is supposed to have an output. We are now removing every single output, but in this case, every single element of the codomain is the output of something. As we're performing this removal process, right? As we can see, for example, in this instance, right? If we remove A, well, on the other side we remove 1. If we remove B, we remove 2 and 3. And if we remove C, well, we're done. We remove everything from the codomain, and now we remove 4, which is in the domain. And that means that we are done. We have absolutely nothing on both sides, right? But something that is remarkable here is that we have to say that every time that we remove something from this site, we remove at least something from this site. So, what can we conclude? Well, we can say that there, in terms of a numerical relation, there are more things in A than there are things in B, potentially. Right? And I'll put this kind of in quotation. Well, this idea motivates the following definition. This codification of numericity, right, of collections. Definition. So I'll start. Let f be a function from A to B would say that f is surjective, also known as onto, if for each y in B, in the codomain, there is x in A such that y is equal to f of x. Now, I want to stress it again. We can see that this is closely related to the idea of the totality of a function, right? Every element of A is associated with an element of B. In other words, for every element of A, there is a y in B, such that that element of A is associated as an input and output with that of B. Okay. With this, we conclude the notion of surjectivity and a motivation in terms of comparing collections.